Standard deviation is a measure of how spread out the values are around the mean. If it is small, it means that most of the data points in that variable are close to the mean. And if it is large, it means that most data points are kind of more spread out from the mean. Or in other words, it is a technique to standardize the deviation of all the values in a variables from the mean. Okay, let's manually calculate standard deviation using MS Excel. That should clarify this critical concept in statistics. Open the hot dataset in MS Excel and then move your cursor on top of column H, the diastolic variable, until the header turns to light green and the cursor changes into down arrow, and click. That should select the column. Control C to copy the column. Now move the cursor on this plus button to open a new spreadsheet. Click on it. And then in the new spreadsheet, paste it in column A by Control V. Okay. Now we have all the values for diastolic blood pressure in hard data set. In the next column, write mean. We are going to calculate the mean diastolic blood pressure in this column. And enter this formula in cell B2 equal average, open parentheses. Now move your cursor on top of column A until it changes the down arrow and A turns light, the cell containing A turns to light green. Click, or you can just type A:, closed parentheses, enter. So now it is giving us the mean diastolic blood pressure in our data set, 85.36 approximately. Now next, move your cursor to the bottom right of the cell B2, this small square, until it changes into plus button. This is known as fill handle. Let's double click on a fill handle. This will in fact enter the formula in all the cells below that particular cell for which you have double clicked the fill handle. Okay, now we have the average of column A filled in all the cells in column B. Okay, next we are going to calculate the mean, the difference of each of these values from the mean. Okay, so I'm gonna label this column diff for difference equals 78 minus 85.36, enter. So now I see that this person with diastolic blood pressure of 78 has a value that is approximately 7.36 millimeters of mercury below the mean. Again, I'm going to click on fill handle, and now I see that the second person has a diastolic blood pressure 92, which is 6.64 millimeters above the mean. Third person has a diastolic blood pressure of 90, which is 4.64 millimeters above the mean. Similarly, fifth person has a systolic blood pressure 5.36 millimeters of mercury below the mean, and so on. Okay. Now, as we just learned, standard deviation is the average deviation from the mean. We are trying to calculate how much on the average all these values are differing from the mean. We have calculated the difference, but we now encounter another problem. Some of the values are below the mean and some are above the mean. So if we take the average of this all these values, it will be kind of misleading. For example, if I calculate this, we see that this value, whatever it is not giving us any useful information, any meaningful information. Old school method of getting rid of all these negative signs is to multiply these values by themselves. Let's do it and then I will explain. Let's label the column D as squared difference. And let's multiply each of these values by themselves. C2 asterisk, which represents multiply by C2, and enter. So we got the square of 7.36 millimeters of mercury, which is 54.15 millimeters of mercury. It doesn't really give us any meaningful information, but what we are going to do next is we are going to take the difference for all these values and then take the average of it, and then we'll take the square root of it. That should give us the average deviation of all these values from the mean. Let's do it and I will explain once we have done all of them. Okay, we're going to click on the fill handle. Okay, these are the squared values from each respective difference from the mean. Okay, now we can take the average squared difference. Average squared difference, which is going to be average open parentheses d colon d close parentheses. Okay, so now we see that on the average the squared difference of all these values is 168.27 millimeters of mercury square. It is not a very intuitive value, but if we take the square of it, square root of average squared difference, this value should give us some useful information. So I'm going to just take the average of it, square root of this value, which comes down to 12.97. So this value 12.97 is telling us that on the average all these values are differing from the mean by 13 millimeters of mercury. Okay, as we just learned, larger the squared this average value is from the mean, means that the data is widely spread out, and if it is small, it shows that the data is quite narrow, or it is kind of very close to the mean. Okay, we call this average square difference as variance, and this square root of average square difference as standard deviation. Okay, so the standardized deviation of all the diastolic values from the mean is 13.97. Again, if I draw a histogram and kind of smooth a line on it, it should look something like this. Okay, let me draw this. You might get some histogram something like this. Most of the values will be in the center, and lesser and lesser number of values will be on the periphery. But if we have a standard deviation which is larger than 13, say 24, our histogram might look much flatter or much more spread out, something like this. Let me use some other color. Okay, so the spread out might look way more spread out like this. And if we have a narrow standard deviation, say 5, then in that case our data might look much narrow, or something like this. Okay, I just wanted to show you how visually larger standard deviation or the narrower standard deviation might look in a histogram. Z-score is again a very important measure. It tells us how many standard deviations a value is away from the mean. Okay, let's again calculate z-score manually using hard.excel spreadsheet. In the variance column, double click on the fill handle and then do the same for the standard deviation. Okay, in column G we are going to calculate the z-score. It is simply the difference divided by the standard deviation. Okay, and then we are going to fill it in all the cells underneath. Okay, so what the first value is telling us is that the first person has a diastolic blood pressure which is 0.57 standard deviations below the mean, because there is a negative sign there. Let me make it bigger and say this thing again. Okay, if you see the difference is minus 7.36 millimeters of mercury, right? And the standard deviation is 13 millimeters of mercury. So if we divide 7 by 13, it gives us the standardized difference of this value. The thing is that we might have the values in millimeters of mercury or pounds or kilograms or centimeters or milligrams per deciliter, whatever the variable is, the unit of it is going to be different as per the nature of that particular variable. What z-score calculates is, instead of the standard deviation in terms of that particular unit, millimeters of mercury or pounds or kilograms or centimeters or milligram per deciliter, it is going to standardize that difference by a value which is comparable from one variable to the other. I will explain that in a second. Okay, so we see that the second person has a diastolic blood pressure of 92, which is 6.64 millimeters of mercury above the mean. And in standardized term, this difference, 6.6 millimeters of mercury, is kind of 0.5 standard deviations below the mean. What is the use of z-score? I'll show you in a second. We will talk about 95% rule in detail in the next chapter, but I just wanted to give you some idea about it since we already have some momentum towards it. In a normal distribution, which is the case in most of the data we collect in the nature, approximately 95% of the values of the data falls within 2 standard deviations from the mean, that is 2 standard deviations above or 2 standard deviations below the mean. Let's see it in the hard.excel spreadsheet that we were working on. We continue to work on hard.excel spreadsheet. Let's label the column H as 95% rule. Okay. Now enter this formula in cell H2 equals count ifs, open parentheses, column G to G, comma, quote, greater equals -2, quote, close parentheses, enter. Okay, so now we see that of all the values in column G, 5209 values, 5177 values are above -2. Let's add another condition here. The second condition is column G to G, where the values are less than, with quotes, within quotes, less than equal to 2, quote, close parentheses. Okay, And now enter values. Now we see that of all these values, a lesser number of these values are between -2 and 2, that is 2 standard deviations above or below the mean. Okay, so of 5,209 values, we see that approximately 5,000 values are between -2 and 2, or 2 standard deviations above or below the mean. Okay, now let's divide them by the total count of values there. That will give us the proportion of these values which are 2 standard deviations above or below the mean. Count G to G, close parentheses, enter. Okay, so it is now calculating all the values in column G which are 2 standard deviations above and below the mean, divided by the total count. So we see that almost 95% of all these values are between -2 and 2 standard deviations, or 2 standard deviations above or below the mean. And if we now replace this variable diastolic with any other variable, let's say we replace it with systolic blood pressure, okay, and we paste it here. Now obviously the mean is different for systolic blood pressure than it was for diastolic blood pressure, and of course the difference for each of these values is going to be different. Square difference is going to be different, variance is going to be different, and all these values are going to be different. One thing which has not significantly changed is the 95% confidence interval, which stays very close to 95%, right? Again, all these values are 2 standard deviations above or below the mean, right? Let's replace it with, say, cholesterol level, okay, and see what happens. Okay. Again, everything has changed, but we see that all these values are again 2 standard deviations above or below the mean, right? 95% of them, very close to 95%. Not always this rule holds very tight. For example, say age at start. Okay. In this case, we see that almost all of them were within 2 standard deviations. But you will see in statistics, in fact, in all the data, that whenever you collect the data just by random chance, the values are going to be following this 95% rule. That is, they will be within certain standard they are going to deviate from the mean by some standard value, which is 95%, right? And this is the basis of pretty much all of the statistical analysis or statistical science out there, and we use this 95% rule to determine a lot of things, as we will learn in the next chapter. Okay, see you in the next video.